at the end of the day on Friday, we were talking about the derivative and its actual meaning when we deal with motion equations. I want for the few moments to leave the boundaries of Galileo's motion equations and talk in a greater sense about what motion equations actually are. Motion equations, in a holistic sense, and that word is here to mean that in a very basic and real sense, a motion equation describes the acceleration, velocity, and position of an object due to the existence of forces acting on that object. Motion equations describe the acceleration, velocity, and position of an object due to forces acting on that object. The reason it's important that we are careful about this is Galileo's motion equations assume that there is a constant net force acting on the object. That is a very limited view. The rest of the world isn't like that. Forces are changing dynamically all the time. So our motion equations have to be larger to be able to encompass a more complicated environment. Therefore, we define the three motion equations not based on a specific equation, but based on calculus. For example, the acceleration is the rate of change of the velocity. dv dt. And the velocity is the rate of change of position. To be completely correct, I should list all of these as vectors to be clear that they are vector values and have direction. However, I want you to understand something here that is not obvious. I use the word rate a lot in class. Rate is any change of a variable with respect to time. That is a rate. There are lots of rates in physics and in all sciences. So anything where the denominator is dt, suggesting time, is a rate. So I use the word rate, but in your notes, you should note that any rate is something dt. Now, there's a whole bunch of things I need to express here that have nothing to do with the exam, but this is what a good college professor would do. First, are you aware that you can write something known as the second derivative? You may or may not be aware of that, but because acceleration is the rate of change of velocity, and velocity is the rate of change of position, it is plausible that you could break this up and do substitution. Like so. There is a general kind of not subscript, there's a general kind of notation used here to describe the second derivative, and it looks like this, where basically they treated it like it was a set of variables, and the bottom was squared because it was two different dt's squared, and then they squared just the d because there was just two d's. That's not really what's happening here, but this is the notation they would like you to use. So this represents the second derivative with respect to time. So we take the position function and take its derivative twice. Remember, derivative is just a process. Now, that's not all I want you to know. In college, they won't write it out like this. A lot of times they will use a shorthand for derivatives. Since all of these derivatives are based on x, there is a shorthand for this They say that since velocity is the first derivative with respect to x, they'll write velocity as x with a dot above its head. Single dot means first derivative with respect to time. It's a lot easier to write that than all the fancy fractions. That, of course, means that acceleration is the first derivative with respect to velocity, or, and this is the most common, the second derivative with respect to position, x double dot. Professors are going to assume you know this without ever teaching that to you, and they're going to expect you to know it when you just walk into college classes. However, your calculus teacher does not use those at all, and I'm not going to use them either. Not because I don't want to, I desperately would like to write them, but because the exam doesn't. But if you skip physics in college and you start going into your upper division classes, they expect you to know this. So every once in a while, I'm going to bring it back up just to reinforce it, that this dot notation is very common in college, and that's what they want you to use. Okay. That's really where we left off on Friday, with a little bit of discussion about symbolism. Are you guys ready to learn the new stuff today? Or do I need to review some stuff from Friday? Be honest. Okay. There was silence. That means I can do whatever I want. And I like it like that. That means I can teach anything. So today, what I'd really like to do is talk to you a little bit about how we're going to use this information. But to do so, I need to speak to you about the antiderivative. Not the integral, the antiderivative. What I need you to be able to do is I need you to go in both directions. So to understand that, I want you to think for just a moment. Let's say I have v equals 6t squared plus 7t. That this is my expression for the velocity. I should have no difficulty asking everybody in the room to provide me with the acceleration. In fact, I'm going to give you about a minute, and I'm just going to choose one person at random to tell me what the acceleration is. 40 seconds left, because it took me 20 seconds to spit all that out. I'd say we're down to 30 seconds now. I'd say we're coming in on 20 seconds left. I need to choose my victim. I'd say you have less than 10 seconds. And here we go. The victim is... Okay, Annika, can you tell me what the acceleration is, please? Is there an Annika in here? This is period 4, right? Oh, you must have changed classes. Which means I have to switch over to Harshal. Sorry, you're the next person in line, because the dot was between them.
I got 2t cubed plus 7t squared plus c.
You went the wrong direction. To go from velocity to acceleration, we just have to take the derivative. You went backwards. You did the antiderivative.
Yeah.
Yeah, I'm just looking for the first part, the easier part that we learned last week.
Then it's 12t plus 7.
Yep, that's what you had to do. So Harshal actually went a step further, and that was to actually talk about the antiderivative. But for right now, I was just doing what we did on Friday. So to get the derivative and find the acceleration, you would do the process that we talked about for polynomials. Now, do I need to review that for anybody in the room? Or anybody at home?
Yes, please.
Out there and let me know where I was. The derivative of a polynomial is relatively easy to do, but it takes a formula. You have to know. Now, the truth is, there are lots of different derivatives out there. So I want to take the derivative of the velocity, which means I want to go d dt of this whole equation. The derivative is like any function. It can be taken of both sides of an equation. So I can say dv dt and then d dt of everything here. So I've applied it to both sides of the equation. Also, it obeys the distributive property. So I can distribute it to each term in my polynomial. Like so. So when I take the derivative of the velocity, I'm trying to get the acceleration. And to do so, I'm going to apply those simple rules to get to this point where I have a single nomial of my polynomial, a single term. Now, you could have, and you don't have to write this down, you could have a situation where you have other things here, like plus the sine of 6t plus the logarithm of 15t. You could have all sorts of things. This is no longer a polynomial, right? This has other functions in it. And although there is a rule for taking the derivative of each of these things, we don't need that now, and we won't need it for a while. So assume that all the stuff we're going to have are just going to be straightforward polynomials. And a straightforward polynomial is of the form c t to the n. Right? This is the strict form of a polynomial. T is your variable, c is the coefficient, and n is your exponent. That is the strict form of a polynomial. So a standard polynomial can have any number of terms. However, they're all generally placed in order from highest power to least power. That's the standard way you write out a polynomial. Is that okay with you guys, or do I have to explain that in more depth? What a polynomial is? Oh, good. Because the rule for finding the derivative of a polynomial is relatively easy. If you have d dt of ct to the n, the rule is to bring down the exponent and multiply your coefficient times your exponent. Leave your variable in place, but subtract 1 from the exponent. This is how you find the derivative. It works for polynomials only. And you can only do one term at a time, but you can string them together like we're going to do right here. So, I'm going to go to that first term. That first term requires me to bring the 2 down and multiply by coefficient 6 times 2. Bring back down my variable and subtract 1 from the exponent. That will be the first term in my polynomial. I'm good. Questions about that? Go on to my next term. Plus, there's no exponent on the t. So what is the exponent if there's no exponent on the t?
1.
That's right. There's an implied 1. So this will be 7 times 1 times t to the 1 minus 1. Now you should clean it up. 2 times 6 is 12. T to the t minus 1 is just t to the 1 power. Next, 7 times 1 is 7. T to the 1 minus 1 is t to the 0, which is just 1. Which leaves us as this is the acceleration. Questions about that? So, and at least, let's practice this once more, just for fun, okay? Let's say that I have x as a function of t is 8t cubed plus 4t plus 5. Can you tell me what the velocity is from there? Remember, velocity will be the derivative of position with respect to t. So take a minute, see if you can do this, and then we'll come back together and talk about it. So, who wants to just shout out what that first term's going to be? There you go, 24t squared. Great. Next term? Plus 4. Next term?
0.
Yeah, let's remember, this is supposed to be telling us how each term changes over time. Does the 5 change over time? No, so it would be 0. The derivative of any constant is 0. But if you don't believe me, and there's no reason to take my word on it, apply the rule. There's no t there, though, so what is the implied exponent on t if there's no t there? 0, that's right. So now I apply the rule. 5 times 0, t to the 0 minus 1. Doesn't really matter what happens after I do 5 times 0, though, right? Because 5 times 0 is just 0, and that's why it's eliminated. So the derivative of any constant is 0, leaving me with this answer. Of course, you shouldn't stop there. I mean, you should go one step further and tell me what the acceleration is. Not hard, right? It's just the next derivative. And I really don't want to wait very long here. So, I don't know. Let's see who I can call on. Leighton, can you tell me what my answer is going to be? Thank you. 48t. That's right. Now, this is not what I want you to be able to do. This is half of what I want you to be able to do. What I really want to be able to do is have you tell me where is the object when its velocity is 0. I mean, that's the kind of stuff I want to be able to do. But right now, we're just kind of practicing the derivative and the antiderivative. So we have done the derivative portion. And because I want to be thorough and have you guys have the same experience as 6th and 7th last week, I want you to think of this for just a minute. Look familiar? When you take the derivative of this, remember a and v naught are coefficients here. So if I take the derivative with respect to time, I should be able to treat these just like any polynomial. The bottom variable here in my derivative tells you which thing is the variable, and everything else there is a constant. So when I'm taking the derivative with respect to t of 1/2 at squared, the 1/2 and a are just numbers. They're the coefficient. Bring down my exponent, 2, and then multiply by t to the 2 minus 1. That's the derivative of the first term. Questions about that? Go on to the next term. I'm going to have v naught times 1 times t to the 1 minus 1. This should be the velocity. So when I clean it up, I'll get v equals 1/2 times 2 is just 1, so that's a. T to the 2 minus 1 is just t, plus v naught. You do see what this is, right? Where it comes from? You do recognize those as our Galilean motion equations? that this is a natural consequence of having an expression for x, which is why we can take the derivative of one and find the other. All right, how are we doing? Ingenious folks are. So again, can you work backwards? Can you get x from knowing v? Guess at what the expression must have been before you took the derivative. Got some really smart people out there. I know you can. I know some people in the room have already done it. And of course, some of you had calculus, so you know exactly how to do this. Who needs more time? That's not us. Remember, that's the bell that lets everybody at lunch know it's time for them to go to their class. We get released at the chimes. Yes, we have 6 minutes. All right, let's see. Anybody want to just throw out what they think the answer is? Okay, that's all right. That would have been, like amazing, but it's okay. Let's go term by term. There was something here before, right? Something with t in it. And to get a t squared, I know that I had to have subtracted 1 from whatever the exponent was before. So this should be t cubed. Now, that also suggests that this 6 so you're going to run into all the people leaving the lunch line right now. That's probably not the intent, but this is the way of things. But let me at least get the answer out there for you. This would be 2, right? Because I would have had to multiply it by 3 to get the 6. So I would divide the 6 by the 3 to get the 2. In the same way that this is going to be 7 halves t squared, and this is going to be 4t. But we're not done. There's something else that has to be considered, but we'll talk about that tomorrow.